second day in Chapter 3. We're now in Section 3.2, and we're talking about this thing that we're going to call the mean value theorem. Mean being average. Mean value theorem, here's basically what it says. So I've got this blue function right here. And before we get into what all this gibberish means that defines the mean value theorem, let's think about what this would mean. Looks like I've got this blue function. It's defined on the interval between a and b. And sorry, I didn't mean to write that so you can't see it. That endpoint is included, so between a and b. And so if I came over here and I said, what does this mean? Well, this would give us the slope of the line connecting those endpoints. The slope of the line connecting those endpoints. Or in a lot of the things that we do, this would give us, would give us the slope of the line through the endpoints. Okay, another way to say that, this would give us our average rate of change of this function. Because I'm looking at it, I'm looking at where it started and where it ended, and I'm kind of dividing it by the difference between the two endpoints. So average rate of change. Well then, what does this other thing mean? What does f prime of c stand for? F prime of c, well, let's see. That would be the slope of the tangent line at x equals c. So what this mean value theorem says, first off, you've got to have a function, and that function has to be continuous, which that blue one is, for all the x values in an interval, including the endpoints. And it also has to be differentiable for all the x values in between the endpoints. So if you look at this one, definitely differentiable, doesn't have any sharp turns, doesn't have any asymptotes, doesn't have any breaks in the line. So it's definitely continuous. It's including the endpoints. It's definitely differentiable because it doesn't have any sharp turns or any breaks. Then there's got to be at least one x value, okay, we're calling it c, in this interval. And notice that x value has to be between the endpoints such that the slope of the tangent line matches the slope of the line through the endpoints. And also, if we look at this purple thing, this slope of the tangent line at x equals c, well, average rate of change, this is also the instantaneous rate of change. So this place that we're looking for, if you think about it, slope of the tangent line, how many places on this graph would the slope of the tangent line match the slope of that red line that I have drawn on the graph? Well, looks like there'd be one right about there someplace. Looks like there'd be one right about there someplace. Looks like there'd be one right about there someplace. Looks like there'd be one right about there someplace. So according to this, there would be 4 places that the slope of the tangent line would match the slope of the line through the endpoints. Mean value theorem says if you have a continuous function that's differentiable for all the places between its endpoints, there's got to be at least one place where the slope of the tangent or slope of the purple lines match the slope of the red line. That's the idea. All right, so how do we do this algebraically? We just looked at how we would do it with a graph. How do we do it algebraically? Well, first off, when you come up with a problem like this, we're going to check and we're going to say, all right, does this thing fit the criteria? Is this thing a continuous function? Well, let's see. We've got negative x squared plus 4. That is a parabola that's opening down. Yes, that is definitely a continuous function. No problem. Is this thing a differentiable function? Well, is it a differentiable function? Well, let's see. We should probably take the derivative and see if there's any problems with it. So f prime of x, I'm going to do this with that purple color because we'll need that eventually. Negative 2x. Are there any issues with f prime of x? Are there any is it going to have any breaks in it? Is there any sharp turns in it? No, there's definitely not. This thing is definitely differentiable, so no problem there. So we jump through both hoops. So now, according to that, this information right here, this continuous and differentiable checks, says there's got to be at least one place where the slope of the tangent line matches the slope of the line through the endpoint. So let's find the slope of the line through the endpoints. So we're going to do f of 4 minus f of negative 1 all over 4 minus negative 1. And if we clean that up, f of 4, let's see. So f of 4, I've got 4 square it, 16 negative. Oh, and then add 4 to it. Sorry, that should be a negative 12. Minus f of negative 1. So negative 1, square it, positive 1, negative, plus 4 would be a 3 over the top of a 4 plus 1, which would be ultimately a 5. So what we really have with this red number is we're looking at negative 15 over 5. So this slope of this tangent line through the endpoints is really negative 3. Well, according to this, there's got to be at least one place where my negative 2x has to equal my negative 3. So if I solve that equation, I'm going to end up with an x value where all this happens of positive 3 halves. Positive 3 halves. If you want to illustrate that for yourself, you've got a parabola opening downward, and that parabola opening downward, and we're looking at a slope of negative 3, so this parabola must look something like this. The red line must look something like that, and my purple slope must be somewhere in here. That's kind of a visual of what we found, and I know I didn't put any specific points on it, but that's what we just figured out. Problem number 2, if I kind of do the same thing, find any x values that satisfy the mean value theorem for fx equals x to the 2/3. Let's do the same thing that we did before. Is this thing continuous? Well, is it continuous? Let's see. So x to the 2/3 power. Well, it doesn't have any asymptotes. And x to the 2/3, well, there's not. It's going to exist everywhere because you're taking the cubed root of something. So no problem with continuity. This thing is definitely a continuous function. Differentiable, on the other hand, well, let's see. Differentiable, if I do f prime of x, how about 2/3 x to the negative 1/3 power, or 2 over 3x to the 1/3? Well, is there any issues with that? Well, that would be discontinuous. That derivative would be discontinuous at x equals 0. So x cannot be equal to 0. This function would not be differentiable at x equals 0. Is x equals 0 in our interval from negative 1 to 2? We're doing the interval from negative 1 to 2, and x equals 0 is in that interval. So this thing is not differentiable at x equals 0. Mean value theorem does not apply on the interval from negative 1 to 2. Now, interestingly enough, what if the interval instead would have been going, and it would have been different? What if the interval instead of being negative 1 to 2, what if the interval was, let's see, how about if we went from 0 to 2? Well, then mean value theorem would be okay because it would not be differentiable at x equals 0, but that's all right. It's got to be differentiable at all the places in between the interval. What would we look at right here? Then we could apply it. So what you're looking at with the mean value theorem, it's got to be continuous for the whole interval. It's got to be differentiable everywhere between the endpoints. So that's why looking at this interval down here on the bottom, that's why including 0 as an endpoint would be okay, because it's not differentiable there, but we could still apply it. We could still make this go. So that would be mean value theorem.